there are a few, 2 or 3 lectures in which the main challenge is to be able to see the forest through the trees, meaning that to get the message and not get swallowed by the mathematics. This is the first of these lectures, I think. So let's try to, I will try to do it slowly as far as I can. And your challenge is to stop me when you, if or when you lose contact with the general idea. Okay? So, we were started with the area equation. This is something we did in the last lecture. And we want to find the asymptotic solution as x goes to infinity. Asymptotic solution means we want something that will be asymptotic to y as x goes to infinity. That's our general goal. Now, to do that, we have suggested a trick, and now I will follow what, I will recite what we did in the last lecture, and we'll continue from this point. So the idea was to write first y equals to e to the s of x. This is for free because, we can always write such a thing once we didn't specify x. Okay? Then, by the way, what's the intuition behind this? We have the feeling that close to infinity, y is doing horrible things. So instead of studying y, we would like to study the logarithm of y, because maybe y is doing horrible things. Logarithm always makes horrible things to be less horrible, so we want to see what will be the answer. And we find out that the equation now is s double prime plus s prime squared equal x. This and this are the same equations, and of course the hardness of solving this is exactly like the hardness of solving this, because there is a law of conservation of hardness, and we didn't do anything by taking this, by plugging this expression. The point is that now we replace the equal sign by s double prime plus s prime squared is asymptotic to x as x goes to infinity, and now we are in a much better shape. Because what we can do now is what we did in the last lecture. Dominant balance analysis. We have 3 terms, but we have the feeling that only only 2 of them will balance each other as x goes to infinity, and the other one will be negligible with respect to this term. And we did find in the last lecture that the terms that are dominant as x goes to infinity, so the behavior at x goes to infinity is governed by the balance between the s squared and the x. S prime squared and the x. These are the 2. We tried all the possibilities, and we figure out this one, which implies that s prime is asymptotic to plus minus x to the 1/2, which implies that s is asymptotic to plus minus x to the 3/2 divided by 2 times 2/3, which implies that s double prime, I'm writing it for reasons that will be understood immediately, is asymptotic to what? To plus minus, this is f prime, and we should take the derivative, so we have 1 over 2 square root of x. Okay, now, this finding suggests us that the asymptotic behavior is because s is asymptotic to plus minus 2/3 of x to the 3/2. then we expect y to be asymptotic to e to the plus minus 2/3 x to the 3/2, because y is a e to the power of x. But as we stressed in the last lecture, while this is true, this is true, this is not true. Why? Because if a function is asymptotic to another function, right, if f of x is asymptotic to g of x at x goes to x naught, this does not mean that e to the f is asymptotic to e to the g, and the reason is because asymptotic means that the limit of f over g is going to 1 as x goes to x naught, and this is fine. But to say that the limit of this divided by z is going to 1 is to say that e to the f minus g is going to 1, which implies that f minus g is going to 0 at this limit. Right? So this is not, we cannot write this asymptotic sign unless we make sure that what?
That that they approach 0. That they approach each other.
That the correction, right? There is a correction to that. I mean, unless we are making sure that this minus the actual divided by the actual y is going to 1, and this implies, if you write it as an exponent of something, that I mean, if we will write it as e to the a plus b plus c plus d, something functions of x, when one of them is going to 0 as x goes to infinity. Right? We should make sure that what we neglect are only terms that are going to 0 as x goes to infinity. Do you understand? This is a very crucial point. Good. So, we have to calculate the next term and to see what the next term is doing when g goes to infinity. By the way, the technical name of this first term is a controlling factor. And by calculating the controlling factor, we did a very important step. I mean, this is very similar to the behavior of the A function is going to 0, like e to the minus 2/3 x to the 3/2, and the Bailey function is going to infinity, like e to the plus 2/3 e to the 3/2. It's a very important step, and it gave us a lot of information. But strictly, still, we cannot write the asymptotic sign until we make sure that the next terms are actually going to 0 as x goes to infinity. Okay? Good. So this is a controlling factor, and now we would like to calculate the next correction to the controlling factor. How are we going to do that? Okay. So we know that S is this, and the next correction is negligible with respect to that, right, as x goes to infinity. Okay, so we can write here plus minus 2/3 x to the 3/2 plus c of x, where c of x is negligible with respect to x to the 3/2 at x goes to infinity. And by the same token, I will write here plus c prime, and I will write here plus c double prime of x. Where in each of these relationships, the blue is negligible with respect to the black as x goes to infinity. Okay? Good. Now, what I have to do, I'm going back to my equation, which is this one, right? This equation. I'm going back to this equation, and I will plug my terms here. So, let's write it. So we have s double prime, which is plus minus 1 over 2 square root of x, right? This one, plus c double prime. Okay? But I know, okay, let's write it, plus c double prime. Plus, now I have s prime squared. So s prime squared will be what? Will be x plus minus 2 square root of x c prime plus c double prime plus c prime squared, sorry. All this will be equal to x. I just plug both the blue and the black into the original equation. Okay, what can I say now?
Can you explain again what exactly, what are you trying to do?
I'm trying to calculate the next correction.
Yeah, but why?
This is the controlling factor, right? But of course, this is only the leading term as x goes to infinity, right? And if I'm writing that, it implies that I assume that the limit when x goes to infinity of e to the plus minus 2/3 x to the 3/2 divided by y is going to 1. And I have absolutely no proof that this is the case. In order to have a proof, I should calculate the next term here and show that this next term is going to 0. If this next term is going to 0 as x goes to infinity, then fine. Then I'm in a good shape. Okay? So what I'm doing now, I've added these three things and I'm trying to calculate the next term. Okay? So first of all, this x cancels with this x. It's not an incident. It happens because this is the first order, right? So this x is going out with it. Okay. Now, what I do have, what remains? Okay. Now I know that c prime is negligible with respect to x to the 1/2, which implies that this is negligible with respect to z. You see? Because this is square root of x c prime and this is c prime c prime. So I can neglect this as x goes to infinity. Okay? And c double prime is negligible with respect to z. Okay? So I can neglect this as x goes to infinity. So what remains is an equation for c prime. And the equation is c prime is equals to no, because it goes to the other side, right?
So minus.
So minus 1/4 x. Okay? So very good. So I have calculated c prime. C prime is 1/4x. What is c?
Natural log of x over 4.
So it's a minus, right? Minus 1/4 of x. What is c?
Minus natural log of x over 4.
Minus 1/4 ln x. And what is c double prime?
1 over 4 x squared.
In a plus now.
Yeah.
Right? So plus 1/4x squared. Okay? You see? Which implies that now I can write y in a better way. I have 2/3 x to the 3/2 minus 1/4 ln x. Right? Now, what is 1/4 ln x? E to the minus 1/4 ln x.
X to the minus 1/4.
X to the minus 1/4. So another way to write y is x to the minus 1/4 e to the plus minus 2/3 x to the 3/2. I mean, this and this are the same. And sorry, I'm doing that. And this I am calling. Okay, so this is. I told you this is controlling factor, and these two together are technically called physical optics approximation. Okay? Because this is linear optics and this is physics. This is physical optics, to be honest. Okay, but that's what people, when people are saying we are doing physical optics, they mean that we have calculated the first two terms in. Okay. Now, so first of all, you can see. Okay, now we can judge what we, I mean, before I said to write y is asymptotic to e to the plus minus 2/3 x to the 3/2 is dangerous, right? Because I have to make sure that the next term, the next correction is not, should go to 0 as x goes to infinity. Okay? So now, what you can say about the, so was it true or not true?
True. No.
No.
Not true.
No. Ln x is not going to 0 as x goes to infinity. It's very small, it's logarithmic, but it's not going to 0 as x goes to infinity. So this, to write this was wrong, and now we have better approximation. Okay. Now, is that right? Can I write x to the minus 1/4? Is that correct?
You need to check the next.
I need to check the next step. Very good. Thank you very much. So, I will add here d prime, I will add here d, and I will add here d double prime, and everything is going to be done again. So, I'm going to plug that here. So what I obtained plus minus 2/3 x to the 3/2. By the way, everything that was used in the last step is not going to be used now because it will cancel. But okay, minus 1/4 ln x. Sorry. I need s double prime. S double prime is plus minus 1/2 square root of x plus 1/4x squared plus d double prime. This is s double prime. Okay? Now I have to add to this s prime squared. What is s prime squared? S prime squared is x, which is this squared, plus minus 1/2 square root of x. I'm correct? This and that. Right? And what is the next term? I have this squared. This is that squared. Now I have 2 this times that. And now I have that squared, which is plus 1/16x squared. You see? And now I have plus minus 2 square root of x d prime.
Plus d prime.
Wait. I have this squared. Okay, now I don't need this squared because this is clearly smaller than that. Right? I have this times that times 2. I have this times that times 2. And I have this times that times 2. But I think that this is, okay, let's write it. So I have minus 1/2x d prime. All this should be equal to x. Again, the same thing. Right? Okay? Now, again, the x and the x cancel because this is okay. And what about the next? And we have the 1/2 square root of x. What's going on with the hands today? The 1/2 square root of x cancel with the 1/2 square root of x. This is a second. And now I have to find, and this is negligible with respect to that. And this is clearly negligible with respect to that, as x goes to infinity, right? So we can explore that. And of course, the d squared also negligible. So what we find out is that 2 square root of x times d, this term, right, is equals to 1. I have 1/x squared, and I have 16
5 over
plus 4 over 16, so 5 over 16x squared. With a minus sign, I have plus minus, so I will have minus plus. I think so.
It's a d prime.
What?
D prime.
D prime, yes. So d prime is 5 over 32 times x to the 5 half with a minus plus sign. Okay? And this implies that d, what is d? It's the integral of that. Right? So it will be x to the minus 3 halves, right? Times, and I have to
10 divided by 100.
so I have, okay, so I have here x to the 3 halves, right? And I need, I want 5 over 16, 5 over 32, sorry, times,
2 divided
over
by
3.
5.
Minus 2 over 3.
Oh,
over 3.
5 over 32 should be something times 3 halves, right? Which implies that I have, so this is 16, so I have 5 over 48. I'm not sure about the sign. It's for you to figure out the sign. But this is a very important result. Why this is why this is what I was looking for all the time?
This goes to 0.
Because now I'm getting something that goes to 0 and goes to infinity. So yes, I have to write here e to the plus d, right? But I don't have to anymore because this is, of course, I should put an a here because I mean it's a homogeneous equation, so I can always multiply the solution by an arbitrary factor, but this is actual asymptotic relationship. Okay? So what we did, we calculate 3 orders in this story, and we find out that this is a correct asymptotic relationship. I must tell you that many physicists in many situations are calculating only the controlling factor and don't give a damn for the I mean, others are working hard and calculating also the physical optics answer. And if you are really tzaddik tamim, you go one step further and you calculate the next term. And okay, and if the next term is that, then you are happy because it means that you can stop here. You have the asymptotic behavior. But you may have horrible cases in which the next term is also important. Still, the next term must be negligible with respect to ln x, as x goes to infinity. But for example, you may imagine a situation in which d is ln x. Ln x is negligible with respect to x as x goes to infinity, still diverges, right? So, I mean, this is the case in this situation. Okay, so this is part 1. We have learned how to, we did the calculation up to the point in which it yields for us the correct asymptotic behavior. Now 2 remarks. In the last lecture, I showed you how to solve the area equation in a power series. If you try to use around 0, right? This was a converging power series. Everything was nice, and it was as I said, converging power series. Very nice, but it's an entire function, but now the question is how efficient is this power series, right? So suppose you want to calculate the area, the value of the area function at x equals 10. How many terms you have to take in this power series? It turns out that you have to take many, many terms. I don't remember if it's 10 or 100, but I mean, I think that 10 terms are needed to get to 1. On the other hand, this is asymptotic behavior. I've forgotten, of course, to add as x goes to infinity. Okay? So, how small should x be in order to see a substantial deviation, like 10% deviation from this? Also around x equals 1 or 2. So this is an excellent approximation, right? Although we obtained it using very tricky method, it is much better than the Taylor series, in the sense that for a physicist, right, it gives you the correct behavior of the area function over, you know, I mean, since it comes from infinity, it's also infinite number of orders of magnitude, but in a huge range. Okay, and this is again, this will appear again and again, and there is a reason for it. The reason is that around close to irregular singular points, the function usually is doing horrible things, and if you just catch the origin of this horribility, I mean, like diverging like e to the x to the 3/2, then it gives you very good approximation to the function in a very wide range of parameters. Okay. Questions so far? Good. So, now I would like to implement what I've showed you now, in order, now suppose, okay, I've calculated the first term, the controlling factor, the second term, so I have a physical optics approximation, and I calculated the third term, sorry, to make sure that this is indeed an asymptotic relationship. But what will happen if I will try to calculate more terms? So suppose somebody wants to find the area function at x equals 1/2, or maybe 1 minus 3, but still wants to use the power series around infinity. Okay? What will be the result? Okay, this is so now we are using a different approach. We would like to answer the same question, right? But I want to find, so what I did here, I find first the controlling factor, then the first correction, then the second correction. I can continue, right? I wrote S plus C plus D, and I can add F and G and whatever you like. But instead of that, I would like to do all of it at once. Okay? To do that, I have to work a little bit. And you have to work a little bit because you have to catch my mistakes. So,
wait, now you are calculating the controlling factor in a different way?
No, now I am calculating all the corrections that I have left off. All these corrections are subdominant, are not important at the limit x goes to infinity. But if x is 3, maybe they are correct. They are important. Maybe they give you 20% difference between this and that. So I want to calculate everything like the power series we did for the area. So when we try to expand around 0, we wrote a power series. Now I want to write a power series for the equation, but a power series around infinity. How I'm doing that? So first of all, I'm going to implement what I already have. So what I would like to write is y double prime is e to the plus minus 2/3 x to the 3/2 times x to the minus 1/4 times w of x. So my goal is to find W.
It's already the derivative. We found out.
Sorry, this is Y. This is Y. Sorry. Thank you very much. As I said, you have to find my mistakes now. Right? So this is Y. First of all, let's do a little calculation here. I will say that A is e to the plus minus 2/3 x to the 3/2. Right? What will be A prime? So it will be plus minus the derivative of z, which is square root of x times A. You agree with me? And what will be A double prime, please?
1/2.
So I have to, either I'm taking the derivative here, in which case I will have
X plus
x times A, right? Or I will take the derivative here, plus minus 1/2 square root of x times A. Okay? And I have to make sure, of course, that everything is nice. Yes. We are happy. Not so much. But okay. And now I would like to write, instead of this, I will write it as A of x times x to the minus 1/4 times W. Now what is Y prime now? I have to take the derivative of this triplet, and this will be minus 1/4 times maybe I can write it like, how do I want to write it? Okay, let's try to do it without x, times x to the minus 5/4 times AW plus A prime. Now what is A prime? We don't need A prime. W x to the minus 1/4 plus A times x to the minus 1/4 times W prime. You agree with me? Okay? So what is Y double prime? Okay. What? Let's write it like that. I have okay. I have minus. I'm taking the derivative of this with respect to the x. So I have minus 5/16 plus 5/16 times x to the minus 9/4 times AW. Okay? Now this is the derivative of the first term with respect to the x. Now what will be the next thing? I have minus 1/4 x to the minus 5/4 times A prime times W, but I have to multiply it by 2 because this is exactly what I will get from here if I will take the derivative with respect to x to the minus 1/4. Right? So this is only 1/2. Okay? And then I have minus 1/4 x to the minus 5/4 A times W prime, and again this will be if I will take the derivative here, I include it here, and if I will take the derivative here, it will be included here. So I have 1/2. Okay? So I take the derivative here, here, and here, and it already includes this and this term. Now what remains? Now I have plus A double prime W x to the minus 1/4 So I took the derivative here. And I have plus a prime x to the minus 1/4 times w prime when I take the derivative here. However, this will be also what I will get if I will take the derivative here. So again, I have a factor of 2 here. And finally, I have plus a times x to the minus 1/4 times w double prime. Okay? This is y double prime. Now, what was our equation? Our equation was that y double prime is x times y, right? To remind you, what was the equation? The equation was y double prime equals x times y. So let's see. So this should be equal to x times y. What is x times y? X times y is a of x times x to the 3/4. No, I want to write it as x times y. Okay, now I will start to collect terms. So what I would like to have is an equation for w. I mean, everything is known except of w. So what I'm looking for is an equation for w, and so I will start with w double prime. So I've taken this term and note that I've divided everything by a x to the minus 1/4. Right? So, okay, let's write here a x to the minus 1/4 times w. You see? This is y. And now I'm dividing everything by a e to the minus 1/4. So, so this will become, okay, how should I do that in the most ordered manner? This goes away. Now, okay, let's continue. Now, this is the term with w double prime. What are the terms with w prime? So let's write here plus w prime times. So here I have 2a prime x to the minus 1/4. Okay? But what is a prime? A prime is plus minus square root of x a. Right? So I have plus minus 2 square root of x, and the a x to the minus 1/4 goes away. Cancels with that. So I'm done with this thing. Next, which other term contains w prime? This one, right? So here, if I'm taking out a x to the minus 1/4, what remains is 1 over 2x. You see, with the minus sign, so I have minus 1 over 2x. And I took care of this and that. What remains? Now I'm looking for terms that are order w. What are the terms that are order w? So first of all, I have what are the terms that are order w? Okay. So let's look at this term. This term is a double prime, which is x plus minus 1 over 2 square root of x times a if x to the 1/4, which I've taken out. So I have xw plus minus 1 over 2 square root of xw. The xw goes away with that. So this cancels that. And what remains is 1 over 2, okay. The xw goes away with that. So I have 1 over 2 square root of xw in my deposit from this term. And now, I have to go to these two terms, right? But I have to fill, okay, now here I have a prime. What a prime is? Plus minus square root of x. So from this term, I have minus 1/2. The x to the minus 1/4 with the a goes away. So from the x to the minus 5, I have 1 over x from this. And the quarter goes away. And from the a prime, I have plus minus square root of x. So it will be minus plus, and this will be square root of x. So I have gotten minus plus 1/2, 1 over 2 square root of x times w. That exactly cancels that. Okay, so this cancels that. All these terms go away. And the only thing that remains is this one. That after filtering out the a and x to the minus 1/4, what I have here is 5 over 16x squared with a plus sign. So 5 over 16x squared, all this must be equal to 0. This is the equation. Again, don't let the trees to hide the forest, right? I did blah, 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 blah. I plugged this into the equation, and after the many hand waving and blah, blah, bing, I got this. First of all, please allow me to check if this is actually what is written in my notes. So I have w double prime. I have w prime times plus minus 2 square root of x minus 1 over 2x, and I have 5 over 16x squared w. Okay, so that's fine. Good. So here we are. We have an equation for w. We have an equation for w that I obtained from this substitution. I put this substitution for y for the solution, and I got this equation for w. Now, if I know how to calculate all the terms in w, it means that I solved the problem. But this is against the law, because you can't solve the behavior of you cannot solve exactly the behavior of a function around irregular singular point. Okay. So again, the law of conservation of hardness tells us that this is insolvable, exactly like the damn thing to begin with. Okay. Still, we can try to expand it in a power series. So now I'm doing the same trick. First of all, note that without this term, you see, the equation was solvable. Why? What if I didn't have this term? What will be the name of the type of equations that we have here? I will have w double prime plus w prime divided by x plus w divided by x squared.
It's an Euler equation.
Euler quotient.
Exactly. It's an equidimensional equation, and it will be solved with x, y equals to x to some power. Right? Because here I have two derivatives, so it will be power minus 2. Here I have one derivative, it will be, but I divide by x, so it will be power minus 2. And here I have zero derivative, but divided by x squared, so it will be x to the minus 2. So we know that without this term, x to the alpha will solve the equation.
But at x goes to infinity, that's the most relevant term.
Yes. However, when x goes to infinity, clearly this is the most relevant term. I mean, this is the remnants of the feature that the ugly thing is not going to give up surrender so fast, right?
And we use this, אנחנו משתמשים בשיטה הזאת בשביל למצוא את כל הסקרים האחרים, נכון?
אתה שואל בשביל מה?
לא, אבל אני שואל למה עשינו את זה אחרי שמצאנו את השני ולא הכנסנו אותו לתוך ה...
You're absolutely right. I only want to, I would like to make up a point here. The point is not important for any practical purpose. If you want the behavior of the area and Berry function for large argument, this is good enough. And there is absolutely no reason to spend any effort in finding this correction. The reason why I'm doing that is in order to make a point that is important, right? So, for the moment we are doing sports, right? We are calculating infinite order calculation to something that have absolutely no importance, right? But, okay. So this is the equation we have now. And as we said, these three, this one, and this one are equidimensional, right? So what I'm doing now is I know that if it was equidimensional, it was double x to the alpha, right? So now I will expand it in a power series, but not in a power series in x to the n. So I will assume that w is the sum from n equals 0 to infinity of a n x to the alpha n. Right? Not integer powers. And I will see what will happen. Of course, I'm doing that because I know that this will help us. But again, I'm trying to make a point that will emerge from this calculation. Okay? Now, again, the three red terms are all of them are going to give x to the alpha n minus 2. You see? So I can write now this equation in the following form. Sum from n equals 0 to infinity of the w double prime is alpha n minus 1 times x to the alpha n minus 2 times a n. All of them will give the same coefficient. Plus, minus. Now I have this thing, right? So minus alpha n over 2 plus 5 over 16. All this times a n x to the alpha n minus 2. Do you agree with me? These are the three red terms. Okay? Equals to, now I'm taking only this term and moving it to the other side of the equation. So I have minus plus, and I have 2, sum from n equals 0 to infinity over, this is w prime. So I have to take one derivative. So I will have alpha n x to the alpha n minus 1/2. Why minus 1/2? Because I have square root of n. X. Right? So these three are from the red terms. And this one came from the green term. This one. Good. So, if I would, now I want to satisfy this equation term by term. As usual, that's what we are, okay. So let's see, what, and again, as I told you, I can never solve such a thing, term by term, without writing the first few terms in both sides, right? So what are the first terms to the left? I have n equals 0. This will give me what?
The first 0, it's 5 over 16.
5 over 16 times x to the, times a0 times x to the minus 2.
Right.
You see? Now what is the next term? N equals 1.
It's minus alpha over 2.
I have alpha minus 1. N equals 1, yes, minus alpha over 2 plus 5 over 16 times a 1 times x to what power? Alpha minus 2. Yes? Blah, 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 blah. Is equal to minus 2. And now what are, let's expand it. What the n equals 0 term give me? 0. What the n equals 1 term give me? Alpha.
A1.
Sorry, I should write an here, of course. So alpha a1 x to the power of alpha minus 1/2 plus what will be the next term? This is minus plus, sorry. So the next term will be 2 alpha a2, am I right?
Yeah,
X to the
1.5 alpha.
alpha is now 2,
2 alpha minus 1.
right? So I have 2 alpha minus 1/2. Okay. Now, very important, in such series, a0 cannot, you can always choose a0 to be 1. Why? Because if a0, first of all, you can always multiply the, since again it's a homogeneous equation, you can always multiply the solution by a factor, so we can always normalize a0. And if you are saying, okay, n equals 0 term, a0 vanishes, then you can choose alpha in a way that another n will give you 0, right? So there is no problem in, you can always assume that a0 is 1 without loss of generality. Okay? So this term, I cannot say a0 is 0, right? I must assume that a0 is something, and now the question is, which term will balance this one?
A2.
Now I have to choose alpha. You see? Which alpha is going to balance this term? Okay. So my only option is to choose alpha to be minus 3/2. Because then this will be x to the minus 2 and it will cancel that. You see? So, and you can see, if alpha is minus 3/2, then this is x to the minus 2, and this is x to the minus 2. This is x to the minus 7/2, and this will be, hopefully,
minus 5 halves, right?
wait, this is alpha minus 2, so it's 3/2, 5/2, 7/2.
So,
Right, it'll be 7 halves.
This one will be 2 alpha, which is 6/2, yes, so 7/2, and so on and so forth.
right.
So that's the right way of doing that. Good. So now that we know that, we can write that. Now I would like to derive the recursion relation. Right? I would like to derive A2, A1 as a function. So we have seen from here, right, that 5/16A0 will be equal to minus plus 2 times alpha, which I said is minus 3/2, so it will be plus minus 3/2 times A1. Right? This is this term versus that term. Right? And this will give us A1 is what? The 2 and 2 cancel, so 5/48 with a minus plus here, A0. And from A1 I can calculate A2 because of this relationship and so on and so forth. So my next goal is to find what is the general relationship here. Okay? And it turns out how do I do that? That's it. So the general relationship, please correct me if I'm wrong, is minus plus 2a n no, I want a plus 1. I want to make this, right, to if n is going to n plus 1, right, such that, okay. What's written here, the term is minus plus 2an alpha n x to the alpha n minus 1, right, and we have some of the rank. This is that term. Now I know that alpha is minus 3/2. So I have plus minus here. This will be 3/2. And this will be 3/2 n minus 1. Okay?
Negative 3/2.
What?
Negative 3/2 of the exponent. X to negative 3/2.
X to the minus 3/2. Yes. Minus 3/2 and minus 1. Now, so this 2 cancels with that 2. I have 3 here. Okay? And I would like to write it as plus minus sum over m, where m is n plus 1. Because I've seen that the A0 here determines the A1 here. Right? So m is n plus 1. So I have A. What should I do? Maybe a minus 1. N minus 1. So I have a n plus 1, right?
Right.
Times 3 times 3 times n, which is n plus 1. Okay? And now I have x to the minus 3/2 times m plus 1. So I have 3/2 m. Okay? Minus 3/2.
That's right.
Sorry, there is a 1/2. This is 1/2. This is not 1. This is 1/2. Look here. Right? So So it will be minus 3/2 m minus 2. Okay? So, and now I can compare it with the other side, this one, which is sum from, let's call it now m equals 0 to infinity. It doesn't matter. Now I just change n to m, right? And I have here alpha, but alpha is minus 3/2, right? So minus 3/2 m times, okay, so I have 3/2 m, 3/2 m minus 1. You see? These are these two terms where I take the, plus 1. Plus 1. I took the minus outside. Okay? And now I have plus 3/4 m. Okay? And plus 5/16. All this multiplied x to the an, x to the minus 3/2 m minus 1/2, minus 2. So, okay? So you see, here and here it's the same. Here I just change n for m in order to make things clearer. But now I know what am plus 1 here is, right? So I can write what am plus 1 is, and what is that? Okay, that's pity because anyhow. And therefore, I find out that am plus 1 is what? By just
3 over
right?
3 over 3m plus 1.
I have here, this is am, right? And now I have this thing, so I have 9
Divide by.
9/4 m squared.
You have in the left side 3.
9/4 m squared.
3. And I have a 3. Let's divide by 3.
I will divide. Yes, okay. 3 m plus 1. Okay, this is that. And I have a plus minus here that I have to take into account. I don't remember. Let's say minus plus. I don't. It's not so important. 9/4 m squared from this and that. Now I have 3/4 m plus 3/2 m plus 3/4 m. So this is again 9/4.
8.
No, it's 3/2 plus 3/4. So it's 6/4, but plus 3/4, so it's plus 9/4 m plus 5/16. That's it. Okay. Can we make this a little bit more user-friendly? Yes. So the claim is that this is equals to am times, again, down here I have 3 times m plus 1. And up here I have 9/4. You see this is 9/4 times m squared plus m plus what?
5 over 36.
I have
5 over.
what? No.
No.
I should get 5/16
You
by
take-
multiplying 9/4 by something. So
20 divided by 137.
5/36. Ah, this is what you said? 5/36. 36. And now this is m plus something times m plus something, right? And this plus that should be 1 half, right? So you can check that it's 5/6 and 1/6. Okay. Again, this is a m plus 1 up to this plus minus factor. In one of the cases it will be an alternating series. In the other case it will continue grow. Yes, plus minus.
It's just a gamma function.
What?
We can just get gamma function.
Oh. So now you suggest us, so I have a plus minus here. This is a recursion relation. And now, what this gentleman suggests us to do is to use the gamma function plate.
Yeah, well, it's in principle and multiply by itself.
Wait. I need it in all its glory, right? I wrote it in the wrong part of the black whiteboard. Okay. No. Yes. This is the recursion relation. So now we can say that what is AM? Let's first check that A1. What will be A1? A1 will be A0 times 9/4 times 5/6 times 1/6 divided by 3. So this will be A0 times 45 divided by how do I do that? Okay, let's so the 9 will be 3, and I have 5, and here I have 3 and 4 and 3 and 6. Okay, so the 3 and 3 cancels out, and I remain with 5. No, this was not what I was looking for. Again, 9/4, because we have calculated that, right? Wait. Yes. Okay, first of all, let's take this 3 out, and this will be 3/4. That's for 3. So when I'm calculating A1, I have 3/4, m is 0, right? And m plus 1 is 1. So I have 3/4 times 5/6 times 1/6. So all in all, this goes with this, and this is 2, and I have 5 over 8 times 6, which is 48, which is, I guess, what we found before. Just a sanity check. Okay, so at the end of the day, now we want to write analytically the general term, right? So what will be the general term? So first of all, we will have A0 here with I guess plus minus 1, plus minus 1 to the power of m times A0. And now, for A1 we have 1 here. For A2 we will have 2 here, so this is just m factorial. You see? From the denominator I have m factorial. Okay? And what I have here, and of course I have 3/4 to the power of m. Okay, so I can take this and put it here. Plus minus 3/4 to the power of m. Maybe I will put it in front of everything. So I have A0, and I have plus minus 3/4 to the power of m. And now I have m factorial here. and I should have, you know, for A1 I have 5, 6. For A2 I have 1 plus 5, 6, and so on, and I can use the trick with the gamma functions to get gamma of m plus 1/6 times gamma of m plus 5/6 divided by gamma of 5/6, gamma of 1/6
of the sum.
And it so happens that gamma of 5/6 times gamma of 1/6 is 2 pi. So we can take this out, and we have am equals to 1 over 2 pi times plus minus 3/4 to the power of m times gamma of m plus 1/6 gamma of m plus 5/6. Right? That's a general term. Okay? So this is, this lecture is divided into 3 parts. In the first part, we did the e to the s, and we did the tricks to find the controlling factor and the physical optics approximation, and to show that the next term is going to 0. In the second part, we wrote, where it is? The second part, we wrote y in that way. And now, after blood, sweat, and tears, we have the, we can write w, right? We know what w is. So we can write w that way. And we have a formula for AM. Okay, the only difference is here I wrote it with n, so let's switch back. Instead of m, I will write n. Okay? So we wrote y this way. We have to know w. We wrote w as a power series, and now we have all the terms of the power series in a recursive relationship with only, right, with the only thing is A0, but we can always choose A0 without loss of generality. We can choose A0 to be 1.
Wait, but now we should add 1 in the parentheses. M equals n plus 1.
This is an. No, you have to check. This is the formula for an. Yes. Okay. Good.
Where did the m factorial disappear to?
We have, of course, sorry. I've forgotten the n factorial. You are absolutely right. As I said, your task here, one of your tasks is to find my.
Doesn't this diverge though? Because it has like technically 2 n factorials on top.
Oh, great.
And 1 on the bottom. So does that mean
okay.
It goes to infinity?
Maybe you want to give the lecture, right? So, what's your name? Itai. So what Itai pointed out is that when we did it for the same equation, right, for the area equation, but when we expand it around 0, we have a power series that looks very much like that. I mean, right? We know, by the way, now that we have 3 halves here, right? But we got a power series that looks very much like that. However, and then we've checked whether or not the power series converges, right? This is the next thing, right? Does this power series converges? And we find out that the power series is converging, right? Now what's happened here? Here we have a problem, because if we are now taking n to infinity, right, not x, if we are taking n to infinity, we are going to be in troubles. This kind of thing is exponentially small, with n. I have to replace this also by n. This is going exponentially to 0, and this is n factorial, right? So we have something like e to the something, e to the minus something times n divided by n factorial. That's very good. Both these terms are taking me to 0 as n goes to infinity. However, I have these two gamma functions that behave always like factorial, right? So I have n factorial squared here. And you know that e to the minus, this will go like e to the minus something times n factorial. And since n factorial is going like e to the n ln n, it will win against that, no matter what. You see? Now, by looking at this, I have forgotten the x. But for any x you will choose, like x equals 5, right? The only extra thing here will be 5 to the minus 3/2 n, which is also something that's going down exponentially. You see? So no matter, of course, the larger x you will choose, the bigger will be this term, and it will go down. But at the end of the day, it will go up. Okay? So in general, when I am looking at this power series, term by term, the behavior will be like that. Right? So this will be, now I would like to plot. This is n equals 1, 2, 3, 4, 5, blah, 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 blah. And this is an times x to the minus 3/2 n. Okay? If I will take x to be 100, say, it will give me a huge exponential factor down. And I will have to wait a lot of n's until it will go up at the end. So I will get, if x is 100, I will get, yep, at the end of the day it will go up, right? What will be the case if x is only 10?
Much faster.
Much faster. So it will start going down, but much faster it will go up. And if I will take x equals 1, then I will go like that, and immediately I will go up. You see? That's the features of this power series. So for every x, if I'm now trying, you remember the Taylor series that we had in the last time, for around 0. Around 0 we had Taylor series, and we figured out that it always goes down, right? Okay, this is this series. Let's remind ourselves what happened when we had the Taylor series around 0. Again, this is n, it's n, and this is an, in this case it was times x to the power of, I guess, 3/2 n or something. Yes? Okay? Okay? So, in this case, if x was small, when x was small, I mean, this is, at small x, it went like that, right? If I've chosen x large, then maybe it goes at the beginning up, but then down. And if x is even larger, then it goes like that, and so on and so forth. So in any case, I have to, if I want to calculate something, I have to term by term, right? And if I will collect enough terms, I will be as close as required to the right answer. This is Taylor series. Now this series is doing something completely different. I'm collecting terms, and the more terms I'm collecting, the more I'm getting away from the right answer towards infinity. Okay? So this is a useful series, right? And this appears to be, this is Taylor series, right? And this appears to be useless series, right? right? Because we have something that the more term we calculate, the more garbage we get.
It's just everywhere. It's not even like one of those series that only has an area that's useful.
No, this series is diverging for every x.
Yeah.
Right? It's not that it has a finite radius of convergence. It diverges for every x.
Then what's the point?
Thank you very much. This is the question I was waiting for since the beginning of this lecture. What's the point in doing all this garbage? Right? We spent a lot of effort in order to find the power series and to find exactly what is the recursion relation, and at the end what we get is something which is absolutely useless because it diverges. Ha! Very good. This brings us to one of the main topics of our course. And now, although you are exhausted by all these calculations, I must have some sort of trumpet to announce that we have this series, right? And now this is an asymptotic series. New beast in the town. Until now, you were familiar with Taylor series. Taylor series have the property that the more terms you collect, the better is your situation. If you know how to collect the first 1,000 terms, good. If you know the first million terms, great. And you improve your situation, the more terms you. Okay. And now we have to have we have to get familiar with the new beast called asymptotic series. And we are going to say that if W is asymptotic to the sum from n equals 0 to infinity of an x to the alpha n or whatever, no matter what, right? Let's write it like an x to the n. I mean, but it's in general, right? Again, asymptotic to means at x goes to x naught. What does that mean? That means that in order to, first of all, let's define Sn as the sum from n equals 0 to n of an x to n. What is that? The partial sum. Right? Instead of summing up to n goes to infinity, let's sum up to a capital N, like the first 100 terms. So W is asymptotic to this series if W minus Sn is smaller than a n plus 1 x to the n plus 1 as x goes to x.
So, do we need to optimize to some value of n, of capital N? Like, how do we know?
What does it mean? If you calculate the first 5 terms in the series, the error from the correct answer will be smaller than the 6th term. If you calculate the first 100 terms, right, then the error will be smaller than the 101 terms. Are you with me?
But why don't we just keep the first one?
What?
Like, do we need to get some value of n of capital N, or?
No, this should be true for every n. For every capital N. For every capital N, the error is smaller than the next term in the series.
So why don't we keep just the first?
By the way, not smaller is negligible with respect to the next term when x goes to x naught. The error is negligible with respect to the next term as x goes to x naught. That's the definition of an asymptotic series. Okay? Now, there is a little comment here that is completely, idiotic, but sometimes it does happen that this term is 0. Okay? You calculate the first 50 terms and the 51 is 0, so take the 52. What is written here is not n plus 1, but the next term in the series. Right? Not necessarily the next one in a row, but the next term in the series. Right? Okay, so this is the property of an asymptotic series. Note that asymptotic series does not have to converge. Right? You only say that it's always true that the next term will be negligible with respect to all the terms you have collected as x goes to x naught. Okay, so now, suppose I have calculated all this. I have calculated the ans according to this formula, and I have such a scenario. Right? I told you this is for this is for n equals this is for x equals what?
100.
This is x equals 100, and the green is for x equals 10, and the blue is for x equals 1. Okay? And I want to know what is y at x equals 100 using this series. What should I do? Very good. Thank you very much. So the trick is like that. I've calculated the first term, it gives me that, and I know that the error is smaller than that. But it's much better to calculate the first two terms, this and that, because then the error will be much smaller. And I will go, yes, here, the error still much smaller, much smaller, much smaller, much smaller, much smaller, blah, blah, blah. I will reach this point. Oh, the next one, I will get only a bigger error. You see? So the trick with asymptotic series, right? This is by definition an asymptotic series. And the trick is to use optimal truncation. See? That is to say, I am taking, I'm going with the series until the one before the minimum, right? If the minimum is here, then I want to calculate to stop here, to truncate here, and this implies that the distance from the error, the distance from the true answer is much is small. Here I will stop here. I will stop just before here, like, and here I will stop just before this. That's an optimal truncation. You see? So again, I will try to emphasize. Okay, not in a good shape with time, but I will emphasize that this behavior is not a peculiarity of the area equation as that goes to infinity. This behavior is what you have in all the important power series in physics. All the important calculations of perturbation theory and power series in physics end up not with Taylor series that have a finite radius of convergence, but with asymptotic series that diverge. Usually the radius of convergence is 0. They diverge everywhere, like this. And what should you do in order to, if you want to find what will be, I don't know, the energies of anharmonic oscillator? So now we gave a prescription, right? Take the anharmonic oscillator, expand it around the harmonic oscillator, right? You have a power series. The power series will give you terms like that, and you will stop whenever, you will use optimal truncation to know how to stop. Now, this seems to suggest that there is a finite accuracy for our perturbation expansions. Right? We cannot be more accurate than what we get from the optimal truncation. For every x, or for every level of anharmonicity of the oscillator, say, we cannot be better than the optimal truncation. Right? And that we will have to work hard, because suppose, say, okay, fine, the optimal truncation, but we have to calculate 50 terms, and this is a real headache, right? You want a student to do that, of course. But you are the student, so you have a problem, okay? And, okay, so first of all, as I said, all the important power series in physics are asymptotic series. And now what I taught you today is that your only reasonable way of accommodating with that is optimal truncation, which implies that you have, first of all, you have to work how to calculate many terms, and then that after calculating many terms, there is some mismatch that you cannot avoid, right? And calculating more terms in the series will just will be useless, right? So maybe if you have something like that, only the first and the second term, or maybe you have something even that goes like that, right? In which case, everything is useless. Okay? So there is a, later in this course, I will show you there is a black magic that allow you first to use first of all, to get very close by using only the first 2-3 terms, right? And then it also allows you to use, if you want to get, with a mistake of 10 to the minus 20, then you can use even these terms, the growing terms, in order to calculate them. But this is the black magic, will appear later, right? So for the moment, we arrived at the generic, from this Airy function story, which is important by itself, but Airy function has many applications. But we arrived at the asymptotic behavior of the Airy function as x goes to infinity. We find out that it will be described by an asymptotic series. Okay? Next time, I will elaborate on the properties of the asymptotic series. I'm not going yet to, even next time, I'm not going to show you the black magic. It will appear later. But I will elaborate on features of asymptotic series and discuss the general analytic features of this approach. Right? Thank you very much.
Okay. Hello everyone again. Today we're gonna discuss asymptotic analysis of irregular singular points. So, as you remember from the last time, when we solved second order differential equation like this, we usually may encounter with three types of points. The first one is just ordinary points. In these points, functions p of x and q of x are analytic, so you can easily expand them in Taylor series. The second The second type is regular singular point. So in these points, x minus x naught p of x and x minus x naught square q of x are analytic at point x naught. So with ordinary points we know how to solve this equation. Usually for the regular singular point we use Frobenius method, right? We discussed it last time. And today we're going to discuss third type, irregular singular points. So in these points, these two functions, even after we multiply them by these factors, they are divergent. Okay, they cannot be expressed in a Taylor series. So, and if we can try to apply Frobenius method as we did here to these points, we will see that the Frobenius method will simply fail. So how we can address this problem with irregular singular points? We use asymptotic method, which is I call WKB like method. It's not exactly WKB from quantum mechanics, but it's kind of WKB. So, and we, for this method, we will try to find the solution in the form of e to the power s of x, where s of x can be expressed in this way: s naught of x plus s1 of x plus s2 of x, da da da. So, and usually s naught greater than s1, s1 greater than s2, and so on. Yeah, but for this kind of a WK method, we usually say that our solution is not exactly equals to e to the power s of x, but we say that our solution of some differential equation with ICP is asymptotic to this exponent. Okay. So, and what does it mean that our solution is asymptotic to this?
That at the limit x goes to x naught, it behaves like that. It's the same function.
Yes, and usually then we say that some function asymptotic to another function, we need to specify at which point, right? So, and we say that these two functions are asymptotic to each other at x goes to x naught. Okay. So, let's look at the first example. So this is second order differential equation with irregular singular point x equals
infinity.
Yeah. Right. So again, just a small proof how we can understand that this is actually irregular singular point. We need to do change of variables. We define z equals 1 over x. Okay. Then we need to rewrite this equation into in terms of z. So z over dx will look like minus z squared d over dz. And the second derivative with respect to x equals z to the fourth then we act like these two operators. I mean, we don't need this one, only the second derivative. We will get y double prime plus 2 over z y prime minus 1 over z to the 7th y. Okay. So this is our p function. Q. And z equals 0, it's singular point. Then we see that z times p of z is just 2, so it's analytic. But this one, even after multiplication by z squared, obviously singular at this point. So therefore, x equals infinity or z equals 0, it's irregular singular point. Okay, now let's actually start to solve this problem. So as I wrote there, let's use solution in form y of x if it's not. Then we substitute the solution into equation, and we will get s naught double prime minus
shouldn't there be an s naught prime squared?
yeah, because let's do it carefully. The first derivative will be s naught prime times e to the s naught x, right? Then we take the second derivative, will be s naught double prime plus s naught prime square, and all of these we multiply by exponent. Okay. then we substitute it to the equation. We will get S naught double prime plus S naught prime square minus x cubed equals 0. So this one. Okay. What is the next step?
Checking which thing we can say is negligible.
But as Nadav told you, we cannot really solve this equation. We need to make some tricks, and right here asymptotics, right? So we need to do it pairwise. So we need to check. So each pair. Okay. So for example, S naught double prime. Let's say it's asymptotic to S naught prime square. In this case, if those two are asymptotic to each other, we can neglect this term. Okay. Yeah, and we need to write that we're interested in the case that x goes to infinity. Okay, then we need to solve this equation, right? How we can do it? I mean, we can say that P is S naught prime, okay? Then P prime is asymptotic to P squared. Right? Then we integrate both powers, right? And so x. Then after integration is 1 over p like x. So p like minus 1 over x. And then we go back to this S naught prime asymptotic to minus 1 over x. So was our assumption correct?
No,
No.
Why?
because x cubed compared to 1 over x, just it grows while the other.
Yeah. So we basically neglected this term, but while this goes to 0 and this term goes to infinity, we made the wrong assumption. Okay, so let's try the second option. The second option is to take this and this. Okay, as naught double prime asymptotic to x cubed. Okay. So then as naught prime goes like x to the 4 divided by 4. Okay. And I think in this step we can actually verify our assumption. So,
Right.
Is it good? Is it bad? What do you think? So when we say that this goes like this, we neglected this term. Yeah. So we understand that this behaves like x cubed, but let's look at this one.
Like the prime goes faster than the cube. Like
so it goes faster, therefore we cannot neglect this. So this is wrong assumption. Okay, third one. Tell me what pair I should pick. Maybe you can pick the right one from the.
Yeah, it's the prime. The prime.
This one
squared.
and this. Okay.
Like both of them, right?
Yeah. So we neglect this and say that this behaves like this. Okay.
Exactly.
So then S naught prime is like x to the 3/2, right? And let's compare this term with this. So we need to take other derivative. It's 3/2 x to the 1/2. And it seems to be right. So this grows much slower than these two terms. So therefore, this is correct assumption. Okay, then we know S naught prime. We need to calculate for the solution for this is called control factor, as you know. So control factor S naught is 2/5 x to the 5/2. Okay, so just integrated both sides. Okay, now we know the control factor. Is it enough?
No,
Why?
we have to go to the next order to see that it doesn't explode to infinity.
Yeah, because in the solution we have a lot of terms, right? And we need to show that all of these terms actually go into 0. Then x goes to infinity. Okay. When for the next part we add one more. Okay. And basically do the same calculations. Okay. So we'll have S naught double prime plus S1 double prime plus S naught prime plus S1 prime squared minus x cubed equals 0. Okay, then we need to expand this square root. And because we know what is S naught, what is S naught prime and S naught double prime, we can actually substitute it into this equation. So we have x to the 1/2 plus S1 double prime plus S naught squared just x cubed plus 2 S naught prime, this one, x squared, S1 prime plus S1 prime squared minus x cubed equals 0. You see, here is x cubed plus minus, so we can just skip them. And now we need to use the same logic as we did before. Okay, we need to pick the right asymptotics. So what do you think we need to pick? Now we have much more terms, so we need to do it carefully and wisely. So you see that the correct assumption was choosing this and this. Okay. So
Go to the x with the x.
so we definitely can omit this one using the same logic as we did here, and this was the right logic. Okay. What do you think?
The square term of the derivative with the x term. The linear term.
Yeah, I think that the good choice is to take this.
With the first.
Yeah. Because S1 prime square bigger than this one. Or smaller. So okay. Let's try this. Then we need to write it 3 halves. It's 1/2. Asymptotic to -2 x 3/2 S1 prime. Okay, then S1 prime behaves like -3/4. Here is x to the -1. Okay, then let's decide whether this assumption was a good one or not. So for the square term, it goes like 1/x squared, and so decay much faster than this one. This is right. This one, the second derivative, also contains term 1/x squared, so decay much faster than this. Okay, then this is proper choice. And after integration, S1 is -3/4 1x.
So we need another term. It blows up back to infinity.
But it's in the exponent, right?
Yeah, but it means that we can't. We need
You
to
multiply exponent to the
Yeah, but we still need to check the next term in order so that
Yeah.
in order so that we
yeah.
can say
It's it's better to check that.
because we established that you can't simply assume that they're
Yeah.
asymptotic of that. It's exponent.
Okay, let's check. So we will have S naught double prime plus S1 double prime plus S2 double prime plus S naught prime plus S1 prime plus S2 prime squared minus x cubed. Okay. So S naught double prime 3/2 x to the this 1 plus I'm sorry, minus. It should be the second derivative. No. Or derivative plus. So plus 4 x minus 2 plus s2 prime plus s naught prime square. It's like x cubed. Then this term is 9 over 16 x to the minus 2. Okay. And plus, again, using the same logic, I can neglect the square of this because it will be much smaller than the cross terms. Okay, and the same logic for this term. So then I have two s naught prime and s1 prime. S0 prime is this one, x to the 3 halves, and s1 prime is this one. So it goes with minus 3 halves, and minus 1, so it's 1 half. Yeah. Then, so it was cross term this by this. Then I have s0 prime, s2 prime, and s1 prime, s2 prime. Okay. Again, choosing between these terms, which one we will pick? This or this?
S0.
Yeah, this one. Okay, s0 prime again. So 3 halves. Here is minus x cubed. Okay. Then this is
The first term also. With the middle one.
yeah.
Also, the second and fourth term can simplify.
Yeah, yeah. So here is 12 over 16 plus 9 over 16 will be 21 over 16. So yeah, I have 21 over 16x minus 2. And we have this term and this term. So I think it's clear that we need to pick this one. Yeah. And S2 is asymptotic to, I think with minus. I lost the minus. X to the, it's
Wait,
minus 9 over 2, I guess. Yeah,
No, it's not.
something like this. And after integration, you can see that it goes to 0 when s goes to infinity. So I'm too lazy to calculate this factors, but you can see that it's a constant x to the minus 7. So you believe me. Okay. So I think you solve the area equation with Nadab on the lecture. Yeah?
Yeah.
Okay, then don't need to solve it again. We will solve another example. We need to find asymptotic solutions. Then x goes to infinity. So at the vicinity of irregular singular point. Okay. So as usual, we will solve the problem in this way, starting with S naught. So when we plug this equation, we will get S naught double prime plus S naught prime squared plus 2x S naught prime minus 1. And again, the same, we need to find the terms that balance each other. Okay. So what do you think?
It's maybe like the first derivative, the first two terms.
This and this?
Yes.
We can try to figure out whether it's a good choice or not. Or do you mean that we can neglect them? Ah, okay. So we need to check this too. Okay. And our first assumption will be that 2x S naught prime asymptotic to 1. Yeah. In other words, S naught prime asymptotic to 1 over 2x. So S naught double prime goes like minus 1 over 2x squared. Okay, and the function itself S naught goes like 1x. Okay.
It's squared, right? Instead of a 3.
Good choice. Let's see. So this behaves like a constant, then x goes to infinity, right? This one,
What was it?
this one go to 0. This
was
one
zero.
even Fast? No.
the same,
I mean,
the same.
because square,
Square.
yeah, it's the same speed,
but-
but that's the right choice. Okay. Then we found the control factor. Usually it's not enough for us. We need to calculate more terms. So let's look at the second. So it's not double prime plus S1 double prime plus S not prime plus S1 prime plus 2x S not prime S1 prime minus 1. All of this equals 0. Okay. So it's not double prime. We calculate it. And this S not prime squared is 1 over 4 x to the fourth plus 2 S not prime is 1 over 2x, so just 1 over x multiplied by S1 prime. The last term is S1 prime squared. There is 2x multiplied by S naught prime, so it's just 1, plus 2x S1 prime minus 1.
So to the 4x, the exponent 4, not to the third term.
The third one
Third term you will calculate.
should be S naught prime
Square.
squared. Yeah.
Supposed to be
Just no? I think I did right.
okay. Sorry.
Okay, then this and this. We can also combine these two terms as minus 1 over 4 x squared, right? And again, we need to pick up one pair.
You can also combine the S prime, right?
So okay, let's rewrite that as S1 prime 1 over x plus 2x. Yeah.
Well, you just drop the S prime squared.
Okay.
I mean,
Yeah. So we neglect this and balance these two terms. Then S1 prime asymptotic to 1 over 4 x squared. And here is a goes to denominator 1 over x plus 2x. So 4x plus 4, not 4, 8. Okay.
one. Now we need to check our assumption.
But it will go to 0, right?
Yeah, but I mean, did we make the right choice?
Okay.
I mean, yeah, we already see that if we take a second another derivative or square it, it becomes smaller. Because it's 1 over.
Mm-hmm. Okay. Now we need to calculate S1.
Yeah, at infinity it will go to 0, right? That's the
Yeah.
important part.
No, there's another way. We can decompose it into 2 separate fractions.
Sine 6 goes to infinity. You can neglect 4x, no?
Yeah, but you don't really have to. You can turn it into like a sum of 1 over
I want
x
simple life.
plus 1 over 1 plus x squared. Technically it's 1 over 1 plus 2x squared.
I just think then x goes to infinity.
We can neglect.
Yeah,
For
you
x.
can write it like
And that goes to 0, right? Like the integral.
yeah. That will be like 1 over minus. Okay, then solution is this one and e to the minus okay.
Wait, if we're treating x at infinity, shouldn't it be 4x? Oh, no, I see. No.
It's negligible compared to this. Okay, but we got only one solution. And the original equation is second order. So where is another one?
We can balance the first equation.
Balance the first?
Not the first, that one.
That one? How? I mean, we did the
We did the analysis
right thing, yeah. But somehow we got only one solution.
Maybe you take no. You check just 2 or 1 pairs. You need to check more pairs.
Yeah, let's try to check another pair. Maybe there is another good choice for dominant bonds. So we check this option. What do you think the other good option can be?
Let's see.
Maybe second and third?
Let's see second derivative, yeah.
Second derivative with the
with this
With the second term?
Or maybe
Yeah,
second term or third term, yeah.
I'm thinking about
Yeah.
second and third.
Yeah, the second derivative with derivative squared.
Okay, let's try. I meant this and this, but
Yeah, that's what I did.
it doesn't matter. Okay. S not double prime minus S not prime square. Right? So again, P prime minus P squared. Then we integrate it and 1 over P with a minus here is minus X. Okay. Then S prime goes like 1 over X.
So it gives us basically the same thing, just by a different factor.
Yeah. The same, we will get the no, actually it's we neglect these terms compared to this.
Yeah.
But
You gotta
actually
match the
these
lots of
two
X.
decrease much faster than this.
Well,
So
we gotta
this is
match.
just a constant and this is 1 over X squared.
So it's not good.
So yeah, it's wrong one. Okay. Let's check second and third.
So we can divide both sides by is not prime.
I mean, the proper way to do it is this one. So you write it as S naught prime multiplied by S naught plus 2x. And then you have two choices, but this one is a trivial solution, we don't need it, and second one. Okay. So let's see. This one, I mean, S not double prime, just a constant, we can neglect it. Then one, also just a constant, that's true. And for this goes like x squared, and this also goes like x squared. And
So that's right.
yeah, that's one is right. Okay. Then S naught goes like minus x squared. Okay. So this is the second solution we just in the middle of obtaining. Okay. Then we need to do the same, right? But with S1. I think use this. So S naught double prime is just a -2. -2 plus S1 double prime
cross term,
-4 times
2,
minus 4x. Like instead of the 2,
minus
4x. Like
4.
it's minus 2x, but with the 2 there.
Yeah, minus 4x. Yeah. S1 prime. And then plus S1 prime squared. Then plus minus, I think. Minus 4x squared. Yeah. And plus 2x s1 prime minus 1. Okay, then we see that this and this go away. Then
minus 2. No, you deleted before. Minus 3.
so it shouldn't go, right? Should be minus 2, minus 1, minus 3.
It's S1 prime is we just we keep minus 3 and S1 prime.
Okay. Yeah, makes sense. So we have S1 prime, then here is, by the way, this and this is just minus 2x, and this goes like 3, right? So S1 prime goes like minus 3x. Okay. So the second derivative of it goes like, so we can neglect this and also neglect this because this goes like 1 over x squared, while this just like a constant. Yeah? Okay, then this
The integral, right? S1
1 minus 3 1x. Okay. Good. And then the second solution is x minus 3 half e to the minus x. This is the second section.
But ln x doesn't go to 0 at infinity.
Say it again.
Ln x doesn't go to 0 at infinity. We should calculate the next term. No?
Yes. I mean, you can do it. I mean, if you want, we can do it. I mean, it's not necessary
It's a
for this tutorial. I mean, believe me, it goes to 0. But if you don't, we can repeat this.
Okay.
And it's for me, it's just waste of time sometimes. So yeah. I also have another example, but it's kind of pretty similar to what we saw.
with minor changes. So again, the same thing, but with different x. So the logic is following that it doesn't matter what equation you have. First of all, you, in most cases, I mean, it's not completely 100% information, but in most cases, S double prime is lower than S prime squared. Okay. And S naught greater than S1 greater than S2. So then you look at the cross terms like S naught S1 or S naught S2 or S1 S2. So begin with the bigger one. So this one is bigger than this one, and this one is bigger than this one.
Shouldn't we technically assume the opposite, that the square of the first derivative is less than? Because more often when it's something that decays over time, like if it's the only times it does, like for any 1 over x to any power greater than 1, it will decay faster. S prime squared will be much smaller than S prime prime.
But I guess in these examples we saw the opposite.
Yeah, that is weird.
Right? Nobody said that it's there was a physical problems, you know.
Yeah.
It's just pure math, you know. But you can apply this logic to physics problems. Again, what I wrote here it's for this kind of problems, okay? But, yeah. Okay, then. Do you have any questions about this material?
That's fine.
Okay. So then, today I will upload the second homework. Please to respect the deadlines. If you cannot do it for some personal reason, please write me in WhatsApp or write me email. So then I can postpone the deadline. But if you write me afterwards the deadline, I cannot really help you with.
Wait, don't you mean third homework?
The second one.
No, the first you call it 0.
Oh,
Yeah.
okay.
I did it like a programmer, but
Yeah, but you don't. When you're counting
number
first,
second.
third. Yeah, okay, number 2. Okay.
Yeah.
It's number 3.
But yeah, actually
It's
it's
the third,
the
but
third
it is
one.
number 2.
Yeah,
Number
but
two,
it
it's like a
has
big
number
one.
2. Yeah. So
It's like
okay.
No, but it did technically cover things we
Thank
So
you.
see you next week.
solved
Yeah.
it. We did it so that day, so it was just like really.